Значит, у нас следующий докладчик удаленно. Ну, хотелось бы сначала проверить, на связи ли он. Ага.
Hello?
Do you hear us?
Yes, I can.
Could you increase the volume of your microphone?
Okay. Can you hear me better?
Yes, now it's better. So, thank you. So we may start next
Okay.
talk. Professor Xiaorong Zhou from University of Science and Technology of China will present the project of Super Tau Charm Factory in China. Please, you have 30 minutes for your talk.
Okay, thanks for the introduction. And thanks for the organizer for the kind arrangement. I'm sorry I cannot be there at present due to the visa is passed for the limit for the time. My talk here for the conference and also dedicated to the 7th anniversary of Professor Rubkov is the experimental program for Super Tau Charm facility in China. And first, let me introduce about the rich physics in the Tau Charm energy region. Here, I show the R scan experimental in the energy region from 2 to 7. This is not perhaps this is typically Tau Charm energy region, but the energy region is not fully not so determined. So we call this as the Tau Charm region. And we can find that there are many resonances for the psi, psi prime, psi double prime, and also the charmonium-like states above 3 GeV. There are many topics. For the energy region below 3 GeV, also is a very flat process that the continuum hadronic final states are dominated, and this can be used to study the also several related topics. So to summarize, in this energy region, there are unique features like it is a transition between the perturbative and non-perturbative QCD because it's relatively low energy region, and also there are many thresholds for the pair production of hadrons, like the hyperons and also the resonances and the tau leptons. And we can see above 3 GeV, there are rich resonance structures, and also for the psi psi prime, they can produce with huge cross sections. So in China, we have the base 3 experiment. This is focused on the Tau Charm energy study. However, due to the limited space for upgrading, so we proposed the Super Tau Charm facility in China, which is an extension for the BPC2 base 3 experiment in China. Here, let me introduce briefly about this project. It is with the energy region from 2 to 7 GeV and designed the peaking luminosity of 0.5 times 10 to 35 per centimeter square per second at the optimized 4 GeV. And this is 2 orders of magnitude higher than that of the BPC2. And also it has potential to increase the luminosity and also maybe realize the electron beam polarization in the phase 2 upgrade. Here is the designed layout of this facility with a LINAC of 400 meters and the collider ring of 1,000 meters. And the Super Tau Charm detector is a new generation spectrometer to detect the final states with very high efficiency. The total cost of this project is about 4.5 billion Chinese yuan. And it is with this high luminosity, it is expected to produce the integrated luminosity of 1 inverse attobar per year. So with this luminosity, we expected there are many many particles can be produced. So it can also be called as a superparticle factory with rich resonances and large productions, and also huge numbers for the exotic hadrons. Here we show the comparison of the data set at the super tall charm with 1 year's collection at different energy points, and compare with that of the best 3, BEL2, and some dedicated experiments in the world. We can find the super tall charm can be a particle factory for the light hadrons and the tau leptons, and also the hadrons with the charmed quarks. So we can find the super tall charm has the advantages in many aspects for the data set, and also the clean background and the threshold production and so on. And in last year, actually, before that, we have finished the conceptual design report for the physics and the detector, has been published last year on the frontiers of physics. To summarize, the physics at super tall charm can be divided into 3 aspects, and we shown here. But now we have recognized our goal that I will explain that in later. That the physics at super tall charm can be categorized into 3 aspects. First is to test the symmetry of the basic symmetries, and second is about the QCD study for the strong interaction, and the third is the fundamental parameters of standard model test and measurement. And first part, as I just said, the tests of the fundamental symmetries. We know the discrete symmetries it has played and is playing a crucial role in the understanding of the natural laws. And there is experimental evidence of the discrete symmetries breaking. And here we show the CP violation in the past years that has one great achievement. And the super tall charm with very huge numbers of the kaons, tau leptons, hyperons, and also charmed hadrons, it can study the symmetry properties with high precision on these 4 aspects, or the symmetry on these 4 aspects, like the CP violation of hyperons and charmed hadrons, and the electric dipole moment of the hyperons and taus, and the CPT symmetry test in the neutral kaon system by the Gibbside decay. And also for the rare and forbidden processes, also it can test some discrete symmetries like the flavor numbers and so on. Besides, we are also interested in the evolution of the universe. That we know that with the evolution of the universe, we come into a matter-dominant universe. Like the theorist Sakharov has been predicted in 1967 that there are 3 conditions to break the matter and antimatter and to produce with our current matter-dominant universe. And the second is very important, the CP symmetry. So the study of discrete symmetry is also related to understand the current world in the current universe. And first, let me show you about the hyperon CP violation studies. At the base 3, there is already experiment about the hyperons produced from the Gibbside decay. For example, Gibbside 2 lambda lambda bar, it can produce hyperons with polarization as much as, I think, 15% polarizations. And there are like 0.42 million lambda pairs can be produced. This is not very large compared to the fixed target experiment, but it can give a very precise decay asymmetries due to the quantum correlation of the final 2 hyperons. According to that, the CP test can be constructed with these 2, with the decay asymmetries of the charge conjugate states, and the best CP test has been achieved at base 3. Also, the decay asymmetry also achieved. However, this precision is not close to the standard model prediction currently. The standard model prediction is 10 to minus 4 to 10 to minus 5 for the ACP defined here. And another like the upgrade test of the CP asymmetry in the hyperon decay is to use the polarized electron beam. With the polarized electron beam, the final hyperons has higher polarization, as we showed here, with 0 polarization and 80% electron polarization, or the 100% electron polarization. And we finally deduced about the sensitivity of the CP violation, independence of the number of signal events in the after reconstruction, and the polarization rate of the final hyperons. And it can be found that with 1 year data taken at super tau charm, without the beam polarization, the final hyperon is 10% polarized, and the CP violation is 10 to minus 4%. If with the polarization, the same data set will produce the asymmetry with improved with a factor of 3. So this is the potential to study the CP violation with the polarized electron beam. And also, besides, apart from the lambda process, if we use the cascade decay, with the cascade decay, there are several decay chains for these processes, and apart from the CP asymmetries constructed from decay parameters, the strong phase and the weak phase can be deduced simultaneously. So this can be achieved at the this has been achieved at best rate with current precisions. At super tau charm with 3 trillion gypsy produced per year, the sensitivity of the weak phase is expected to be 0.04 degree. This is comparable with the standard model prediction for the weak phase. And so if at the experiment we can observe any significant deviation from this number, it will indicate a new CP violation beyond the standard model. Maybe help us to explain about the antimatter asymmetry. To summarize about the hyperon CP studies at super tau charm, there are 3 aspects. First, the production mechanisms, the polarization, and the kinematics of the produced hyperons from such electron-positron collider is very clean and is very well understood. And the multiple hyperon, anti-hyperon produced from the gypside decay from all kinds of the hyperons, and that enables us to construct the numerous CP violation observables. Here we show several CP violations observables at best rate. So there are dozens already at best rate for the CP violation observables. And the polarized beam in future may significantly enhances the sensitivity to the CP violation. And finally, but not the last but not the least, is the systematic uncertainty need to be controlled because we are measuring the CP violation in a level of 10 to minus 4. And we can prove that it can be well controlled to a level comparable to that of the statistical uncertainties. So this is a very good advantage compared to the fixed target or the other hadron colliders like the HCB or the Bell 2 experiments. Apart from the decay, also the hyperon electron dipole moment can produce a very high precision test at super tau charm. You can find that here is the production of the hyperon pair from gypside decay, and the form factor of the I think is the HT. It contributed the electron dipole form factors to the hyperons, and we predicted about the predicted about the sensitivity of the EDM for all kinds of hyperons. They can reach a level of 10 to minus 10 to minus 19 to 10 to minus 21. So this is a very, very precise test, a very a frontier precision test for all the kind of the hyperons. Currently, only we have the lambda EDM measurement at the Fermi lab with a precision of 10 to minus 16. And the last symmetry for the CP or CPT related is the K0 bar system. Here, from the gypside decay to the K0 K pi processes, we can reconstruct the flavor tag K0, and also by reconstructing the final state of the pi, the CP of the CP tagging of the K can be determined. And in that way, the time-dependent decay rate of the K0 and K0 bar can be determined, where the CP violation parameters eta plus minus and the phi plus minus are determined. By comparing this phi plus minus with the super weak angle constructed from the mass and the width difference of the K0 bar, we can test the CPT symmetry. And it has been simulated that with the precision phi measured at super tau charm, the CPT can be tested with 1 magnitude better than that of the PDT average currently. And also we have manuscripted the special issue on the CP violation at super tau charm covered the topics I just mentioned here, and some of not mentioned here. The ICAP has been submitted to the Physics Report journal. And also some other rare decay. Here only one example is the charge lepton violation from the tau 2-3 leptons, and this is precision achieved at super tau charm with 10 to minus 9. We can compare that with some beyond standard models predictions, and also process of the charge lepton violation from the gypside decay to E mu or E tau or even mu tau at super tau charm with huge numbers of gypside. This precision can be the world leading one. Okay, here we summarize about the sensitivity of the precision measurement at super tau charm, and also for the rare or forbidden decays at super tau charm compared with some beyond standard model predictions. The second part is the hadron structure and the hadron spectroscopy, because we know the QCD has predicted the existing of the exotic states. So the study of the hadron spectroscopy is the crucial means to exploring the theory of strong interaction. The super tau charm can produce very rich exotic states and offering significant insight in hadron spectroscopy. Also, the quark fragmentation functions describe the quark hadronization, and the electron-positron collider provide the cleanest information. Apart from that, the form factors like of the hadrons of the baryons provide the fundamental observables for these hadrons, also help us to understanding their internal structure information. One example also have shown the great intention is the overpopulation of the charmonium spectrum over its open charm region. And there are many studies recently years, and BES3 also have do many contribution. LHCb and BEL2 has do many studies for these so-called XYZ charmonium-like states. But there still exist the puzzles like the masses of these predictions are very close to the threshold of the to charm mesons and so on. And also we need to understand their production why in the charmonium, not in the open charm channels. And the charge structures like the ZC or ZCS must contain at least 4 quarks, and their connection to the Y state and the X states are not truly understood. So, besides, an overall classification of the exotic states is still missing. So these are all opportunities at super tau charm, as it can produce 1 billion the Y state and 100 million ZC state and 5 million X states per year at super tau charm. And compare with the ISR return method from BEL2, we can find that in each region, the luminosity is less than the super tau charm, not even to say that the efficiency at the electron-positron scan method is much larger than that of the ISR. Also, here lists the opportunities at super tau charm. We expect to draw these questions in future. Apart from that is the pental quark and the doubly charmonium state at super tau charm. This may be studied when we open the threshold above 5 GeV here, because the pental quarks like the gypside to HH bar and also the gypside to lambda C, E plus minus to lambda C D proton, and all these processes, their threshold is opened above 5 GeV, as well as the fully charmed tensor quark with gypside CC bar. It also has a threshold about 6 GeV. So Currently, we do not have the prediction from theoretical side that how large their production will be, but this can be studied systematically at the super-tall charm with a very clean environment. Currently, the results are dominated by the LGCB experiment. Apart from the high energy region, at the low energy region, since we have very large numbers of chip psi and psi prime, and they are very good platform for the globals and the hybrid states. So with this data set, by studying the hadronic final states like light mesons with the UDS quarks, we can study the exotic states and also the pure globals. Currently, the global has been studied at BESS3, but there are still many quantities need to be addressed. So at super-tall charm with the large data set, this can be addressed with the super-tall charm. Then it's for the hadron structure. First is the fragmentation functions. Fragmentation functions, it describes the hadron, one hadron, the probability of the hadron founded in the debris of a hadron carrying a fraction of the parton's moment. And it has been studied at the semi-inclusive deep elastic experiment and other like the hadron colliders. But at the electron-positron collider, they are really studied, and the energy region are mainly focused on the high energy because of the non-propagative features at low energy. But now at BESS3, we are focusing on the fragmentation studies at the low energy and found many interesting results. And it requires a high twist of the QCD calculation. So it really help us understand how quark forms the hadrons. At super-tall charm, since the electron-positron collider provides the cleanest input for the fragmentation functions, it can be studied systematically. And at high energy from 5 to 7 GeV, we can study the charm quark fragmentation functions that cannot be studied currently at BESS3. And these two types of the fragmentation functions can be studied at super-tall charm, the polarized and the unpolarized, the so-called Collins fragmentation functions. So it also gives an important input to the CIDIS experiment to extract the partons distribution functions in future. And for the electromagnetic form factors, this has been extensively studied at BESS3 and also at the CMD and SND experiment. And there are many interesting results found. This is a very important series process studied. But there are still some questions remained in the time-like electromagnetic form factors, such as the step-like behavior and also the damped oscillation distribution on the effective form factor after subtracting the dipole distribution. And the G-Geom ratio showed also a damped oscillation distribution. And also the phase between the G and the GM in the time-like is not necessary to be zero, but we are not it's not predicted of this value. And finally, the asymptotic behavior of the time-like electromagnetic form factors compared with that of the space-like. So at super-tall charm, we just predicted the precisions for these processes. The third part, the last part of the physics highlights is the precision measurements of the fundamental physics quantities. If we look at the standard model, we can find that there are many free parameters that need to be filled in, like the masses of the quarks and leptons, the coupling constants, and the mixing parameters. So at super-tall charm, it can be contributed in quite a few of them. The first one is R value. R value is not in the standard model parameter, but it's a very important physics quantities because it can be test of the colors of the quarks and test the quark model and QCD, find new particles. Apart from that, it can contribute to the fine structure constant and also the muon anomalous magnetic moment. Perhaps not as much as that of the pi processes in the low energy, but for the alpha for the fine structure constant, the energy region from 2 to 3 GeV also play a very important function. And by the ISR method, we can measure the low energy of the pi production and so on to contribute to the muon anomalous G-2. A second part is the tau mass. The tau mass is a fundamental parameter in the standard model. It's listed in the page I just showed before. And apart from that, it is also a very important input to test the lepton universality. Since in this tau mu lepton universality test, the tau mass is of high importance to make it to be limited to improve its precision, because it has a sensitivity to the five orders of magnetic to the mass of tau. And compare with other leptons, currently this mass is also limited with precisions. So with the colliders, there are two methods to study the tau. The super tau charm can use the threshold scan method. It has been proved to with high advantage. Currently, Bio 2 has made the tau mass with the world leading precision, but at Bio 3, also a second round of the data taking has given a better precision than that of the Bio 2. And also a very interesting and important parameter studied at the super tau charm is the CKM matrix. Since it describes the mixing of the quark flavors, the unitarity of the CKM matrix ensures the 3 quark generations, and while any violation suggests there might exist 4. At super tau charm, we can study the CKM matrix of the VUS, VCS, and VCD. Since with VUS, we can study it from the decay of the hyperons, semi-leptonic decays, and the tau decay, and also perhaps the kaon decay, because we know there are some anomalous for this VUS called the Cabibbo angle anomalous. For the VCD and the VCS, with the pure charmed hadron produced at super tau charm, it provides the ideal test bed to study it with high precision. We have been predicted or simulated that about 0.2% precision can be achieved at super tau charm for these two parameters. Okay, above are some brief introduction about the physics at super tau charm. In the later few minutes, I will introduce the status of the R&D activities at super tau charm. First is about the accelerator. Since we know it has great challenges to achieve such a high luminosity at in this energy region. So there are some methods or some technologies has been used with the extremely small bunch size, and also the crabble waste and the other techniques has been used here. Here is some preliminary machine parameters for the super tau charm, and from a preliminary simulation, the luminosity can achieve our request of 0.5 times 10 to 35 centimeters square per second. It's over, but it also needed to be stably running for the high energy, for the high luminosity. And here I show some super tau charm accelerator R&D from the collider ring. The preliminary machine parameter determined with the circumsphere of the 850 meters, and also there are 2 injector designs has been ongoing parallel to study the lattice of this collider, and also the superconductor magnetic has been ongoing, and the rapid frequency cavity has been ongoing as shown here. And in this year, currently the conceptual design report for the super charm accelerator is already finished, and it will waiting for the international review soon. And then it's for the super tau charm detector. The detector has been required from, firstly, we require from the physics part that it needs to have high detecting efficiency and good resolution and very good PID abilities, and also the tolerance to the high rate, the background environment. And here listed the parameter required from the physics part. And also, it's a very general designed detector with MDC, PID using the Cherenkov detector, the electromagnetic calorimeters, and also the muon detector. And here we show the R&D activities of the detector. Actually, the detector is in a good space because good shape because there are several sub-detectors has made the prototypes and they have been doing the beam test the last year. And in this year, we also assume to do the beam test in July and with all the sub-detectors together. So here is some material or the techniques used for all these sub-detectors. I will not introduce them in detail. And for the offline software, we developed use the OSCAR software to study the reconstruction and the simulation and so on for the whole procedure. Currently, the OSCAR works very well, and several full simulation physics process is working ongoing. So under the OSCAR framework, so it can work well, and it can help us to test how robust for the super charm detector design and can we reach a good result or not. Okay, this is offline software. For the site of the Supertao Cham, since Anhui province and Hefei city has supported this project um, very much, and the site is selected to be just in Hefei. Hefei is in the center of China, and the site of the Supertao Cham is in the Hefei Comprehensive National Science Center, located here. It's not very far away from the USTC campus, perhaps like 40 kilometers or so. And the Anhui government has funded the Supertao Cham with 364 million Chinese yuan. Also, we need to apply for the approval from the government since the construction budget is 4.5 billion Chinese yuan. Okay, and so for this geological prospecting and civil engineering design, they are ongoing. So currently, we hope to make all these studies ongoing. And this is a tentative project schedule for the Supertao Cham, and we hope to submit the project proposal to the central government this year, and, because China has also 5-year plan. So in the next 5 plan, hope to do the Supertao Cham construction and then to operation. This is just the tentative project schedule. Finally is the summary. The Supertao Cham covers a unique transition region between the perturbative and non-perturbative QCD, providing precision measurements aimed at answering key questions of QCD and searching for the new physics beyond the standard model. It outlines the challenge, key technology of the accelerators and the detection, and also the data processing, computing, and networking. We are conquer on that. Every province and the USDC has committed support. They're aiming for applying for the construction approval during the 5-year plan. And the international collaboration is crucial, and we hope to construct the collaboration to make a great effort to expand the collaboration work on both domestically and internationally. Okay, here is all from my side. Thank you very much for your listening.
Thank you. We have a time for a couple of questions, please.
This is really great to see the efforts of those physicists like Professor Gersh Brutker and say Professor Bruno Toshak, who were working in the E plus, E minus accelerators previously, may have the continuation in China. Thank you very much for these, discussing your plans. Concerning the physics, would you be so kind to clarify? You mentioned the possibility to study the glue ball efforts. I remember there was the rumor last year from your colleagues from China that there may be the candidate for the observation of some global candidates. Would you be so kind maybe to mention your personal opinion on this and the possibilities on the searches of the global candidates on the theta factory in future?
Okay, thanks for your questions. And yeah, if I understand correctly, you mentioned about the global-like particles observed at base 3, the X2370, I think, because it's a pseudo-scalar, and it has been predicted to be the quantities are very like of global predicted from latest QCD, or it compare it's very similar to that of the eta C, because eta C we treat it as a rich global candidate state. And I don't think this is determined if it is a global or not. So we call it as like a global-like. And in the future, not only at base 3, but also at super tau charm, we need to study their decay properties in the very detailed, because currently it's only studied from the eta prime pi pi or the k short pi process. I forgot. But if we want to determine if it is a global, if we want to remove the like particle word, we need to do much study, not a limit. It's not yet to claim the global has been already founded or not. So we are very careful about that.
Okay, and first of all, thank you very much for this very interesting talk. And my question is about your plan to search for CP violation in baryons. So, do you know if there is any extension of standard models that, first of all, is not excluded from any other experimental data, and second, can contribute to CP violation in baryons in that extent that is still achievable in your experiment? So.
Yeah. Okay. Thank you for your questions. I think there is one theoretical model, the SUSI, has predicted the CP violation of the hyperons in the order of 10 to -3. So this is quite limited at the super tau charm. It can be reachable in the super tau charm study. And there are also some studies from Professor Xiaorong Zhou or his colleagues. Since currently we have found that the LHCb has found the CP violation in the charm, in the D mesons, and it is found to be larger than that of the standard model. So combined with that, they have predicted the CP violation for the hyperons can be also in the orders of 10 to -3 beyond the standard model, and without harm other experimental results.
Thank you. Thank you again.
Thank you.
Our session is over.